I'm going to check my Facebook for new messages and send Rob a goodnight picture of me.
This video is for educational purposes only.
In this video, we will learn how it is easy for bad actors to sniff on your network activity by monitoring your DNS traffic. In order to fully understand the anatomy of this technique, we will learn fundamentals about address resolution protocol, man-in-the-middle attacks, and domain name system. Let's open Terminator and start creating our program. Let's name this DNS Sniffer. Similar with my other videos, I always want to start with a base structure to give me a high-level overview on what the program will look like. This allows me to better understand the goal of the script and make sure that I don't divert from that. So let's construct our base structure. The program will accept user input, so let's import our parse library. Let's initialize the parser object and give it a meaningful description. This will be a DNS sniffer, so let's put that in. Our target is a device on the network, so we will need its IP as a parameter. Let's put some helpful message as well for uniformity. This will be required. Next is we need to indicate the network interface we will use for the attack, so let's add it as well. Put some help message. And same thing with target IP, this will be a required parameter. Before going further, let's make sure those arguments are accessible from each part of the program by calling the parseArgs method. Since we are targeting a device in the network, it makes sense to create a class for it that will include the different methods we will use for our attack. Let's add the init method and put a placeholder. Next is our man-in-the-middle method, which we will discuss further later. Third will be a method for sniffing the traffic. Let's name it capture. Last will be our main method that will drive all the functionalities of the class. This will be the watch method. Then let's allow this program to be run as a standalone script or imported as a module. Let's instantiate our device class and run the watch method. Don't worry if things are still unclear at this point. We will discuss each part in details on the succeeding sections. Finally, let's save the changes and commit in Git. Now let's discuss the core functionality of this attack. The first functionality we need to build is the man-in-the-middle method. In order to do that, we need to understand how this is done and what are the different technologies involved. Devices communicate through each other via the network. They can come in different forms, such as personal computers, mobile phones, servers, smart appliances, and many more. Let's talk about a good example, which is inside our home network. Our personal devices talks to the router in order to access the internet. One of the most common reasons is to search for information and connect to our families or friends in social medias. Man-in-the-middle happens when a bad actor was able to put himself between you and the destination device. He can do all sorts of malicious actions, such as analyzing your network activity. In worst cases, he can sniff on the confidential data, which compromises your personal privacy. So that is the high-level overview on what is man-in-the-middle attacks. Now let's get more technical to see how this attack is carried out. There are multiple techniques that can be used. In this video, we will focus on ARP spoofing man-in-the-middle attack, as it is one of the simplest techniques a bad actor can do. As the name implies, this is based from address resolution protocol, which is part of layer 2 of OSI model. This allows devices on local network to communicate with each other. That is through a layer 2 device, which is basically a switch. Each device has its own network interface card that performs the packet processing. The NICs has their own unique identifier called MAC address. A MAC address is 48 bits long. The first 3 octets is the manufacturer's organizational unique identifier, or OUI. This is an important information for attackers, as this can disclose the type of device for better footprinting. The last 3 octets are network interface controller specific. On local network, the devices use their MAC addresses to communicate with each other. Since these are physically connected devices, the switch has a record on what MAC address is connected to its ports. When a device wants to send a packet to another device, the switch will look at the destination MAC address. Since he knows the device is connected to him, it will forward the packet to the appropriate port. Question is, how does a device know the MAC address of the destination? In order to do that, the source device sends a broadcast message to all devices on the network asking for it. This is called ARP request. Assuming all devices in the network behave correctly, the legitimate destination will reply to the source telling him it has the IP address he is looking for. This is called the ARP reply. The source device will update its ARP cache to take note where the IP address resides. And that is how he knows the MAC address associated with an IP address. Like any other protocol, ARP has its own weakness. If an attacker was able to insert himself in your network, he can maliciously send an ARP reply to attract messages not intended for him. When that happens, he can easily sniff the messages going between two legitimate devices. He can do that by first forcing the message to go to him using the malicious ARP reply technique. Since the attacker is now holding the message, he can open it and view the sensitive content. After viewing the contents of the message, he will forward this to the intended recipient. So that is how man-in-the-middle, using ARP spoofing, is carried out. This attack is very easy to do on local network as you only need to know the IP address of the two devices communicating with each other. In this video, we will sniff the network traffic between a mobile phone and a home router to monitor the sites being visited by the user. We discussed so much high level and theory. Now let's get back to our terminal to put this into action. Scapy, a Python library for packet manipulation, and other network attacks provide an easy way of performing an ARP man-in-the-middle attack. That is by using the ARP MITM function. So let's import that. Let's go back to our MITM method and call that function. We need to pass the two IP addresses we want to sniff. This can be in any order, but let's start with the router IP, then followed by the device IP. Next will be the interface we will use for the attack. We don't have an argument for the router IP yet, so let's add that as well. These parameters are not yet initialized within our class, so let's do that. And on the main function, let's make sure we pass that when instantiating our device. Our main method for driving the attack still doesn't do anything, so let's put some code here. The Scapy MITM function is a blocking call. That means when that is executed, the next instructions on our code will not run. So let's run this on its separate thread so we can make our program asynchronous. We will use the threading module and pass the MITM method as the target function. Then the argument will be blank since we are not passing the IP addresses and interface directly to that method. Finally, let's don't forget to run the actual thread by calling the start method. There will be another instructions that we need to put here, but we will come to that part soon. We will import the threading module since we still haven't done it yet. Before going further, let's give this a quick try to make sure the MITM Scapy function is working as expected. Doing a quick look on the argument seems fine as it displayed them correctly. Now let's fire this up and use my home router and mobile phone for demonstration purposes. Target IP will be my phone, then followed by my home router IP. And let's use ETH1 of my Kali to do the attack. Could not resolve. Well, this error is misleading as this might sound like a DNS resolution issue. But we are still operating on layer 2, so we don't really care about DNS at this point. Looking at Scapy code, the exception that has been raised came from this line. That's because it was not able to get a valid tuple containing the MAC and IP address mapping. That tuple should have been returned by this function. I would guess this ARP ping was not able to get a valid response within the expected time. This is normal on personal devices sometimes as they go into sleep mode. In the back end, that function sends out ARP requests to all devices in the network to find who are online. That is just the same on what we discussed on the previous section. I'm going to make sure my phone is active and we'll try a few more times. Now that looks good. These asterisks indicate that it is sending out ARP traffic to the network, but we can't really see anything yet here because we still haven't built our function to decode those messages. That will be the topic for the next section. We can also see it is showing us my Kali MAC address sitting between my iPhone and home router. Before we conclude this part, I think it would be better if we can handle the exception inside the script. So let's create a loop and make sure it retries the method if it encounters the same error. We'll run this indefinitely. Then let's put the try block inside the loop. Let's just say the IP is not up yet, and we will just retry. Then continue with the next loop iteration. In this section, we will build our method to decode the DNS traffic. Our MITM method we just created allows us to divert the packets from its original path to a malicious path. That means the packet is effectively passing through the attacker's network interface. Since those packets are within our reach, we can now sniff them and manipulate them however we like using a different method. That will be our capture method. We can easily do this in Scapy using sniff function. We need to pass the network interface to sniff, which is same interface used for doing the ARP spoofing. Then we need another function that will do the actual packet processing. Since this is a DNS sniffer, let's pass the packet to a method with same name, which we will create in a second. We only want DNS traffic, so let's use a BPF filter to capture UDP packets on port 53 originating from our target IP. BPF filters are powerful syntax, so I suggest you learn this if you are interested to learn more about packet processing techniques. Now let's create the DNS method. We will put the DNS record in a variable and extract the DNS layer query name from the packet. These classes are still part of Scapy, so we need to import them later. These are in raw bytes, so let's convert them into string using decode function. They contain a dot at the end, so let's strip those unwanted characters. It is also useful to put a timestamp on each request, so let's create that. We'll use the strftime function using this format. Then we will use that format to get the local time. Finally, let's create the print statement that will display the DNS records. From the leftmost side, we will display the time in green font, followed by the target IP in blue, and finally the DNS record in red. We need to reset the styling at the ends so that the color of the next print statements will not all be red all throughout. Most of the required code are already set, so let's import the modules and classes we used on the methods. Let's start with for and style functions from Colorama module, then followed by strftime and local time from time module. And let's add sniff and DNS from our existing Scapy import. I see some minor issues, so let's fix them. The DNS method needs to accept the packet object, so let's add that as a function parameter. Then let's fix this small typo on the print statement. Lastly, let's run the packet processing within its own thread. This is the main reason why we are using multiple threads here, so that MITM won't block the capture method. Now it's time to test this. Let's just execute same command we used a while ago. Be patient. It starts by sending out ARP messages targeting my mobile phone. At this point, we can see that ARP spoofing is working as we see the traffic flowing already. And yes, based from this, you can infer that I'm using an iPhone since it is talking to Apple domains. You also see DuckDuckGo here because I'm opening it as I speak. I'll try to open up an email. Based from the domain my phone is talking to, you can easily know what email provider I'm using for personal use. I'll try to browse some social media sites. This is another important information for bad actors. They can monitor what social media accounts you are using. They can use that information to perform additional OSINT. For example, they can find out from your Facebook profile where do you work and see if you are an easy target for phishing. Aside from social media, a bad actor can also observe other sites you regularly visit. He can also use this information for a targeted phishing attack. For example, if you are recently visiting car dealership sites to buy a new car, he can modify his phishing payload to look like a promotions deal. There are plenty of other malicious things bad actor can do. Example would be finding the type of device you are using in order to create a suitable malware. He can also monitor if there are obsolete devices on your local network you are talking to, which can also be another target for remote code execution exploits. Or he can just stalk you for personal gain. So, in a nutshell, your DNS traffic gives attacker a bigger edge over you, so you need to be aware of this. Now that our ARP spoofing attack is working, the next question is how can we determine the IP of other targets on the network? The idea here is to scan everything locally. So, instead of passing single IP, we will pass a network address. Let's provide a useful description with an example to make it clear what the argument expects. Now let's discuss the scanning part. Scanning devices on the local network is easy. You can send a broadcast message to all devices in the network. Each message is just a normal ARP request. If it receives an ARP reply from a device, it means the target is online and reachable from the network. The process will repeat, and for each iteration, the target IP address is incremented by 1 to cover all addresses in the network. This is called ARP ping, which is a common device discovery technique on local network. This is sometimes referred as ARP scan. So let's create a function with that name. It will accept a network and interface as arguments. We can easily perform this in SCAPI using SRP function, which means send and receive packets at layer 2. Since we need to do a broadcast message, the destination MAC address will be in this format. Then on our destination network will be the subnet specified on the command line argument. Let's specify some timeout. The interface will be the same we are using for the attack. This will return both packets that received a reply and those who didn't. We only care about the online host, so let's store that result in a variable and discard the other unanswered packets. On the next line, let's put some useful header to signify the start of the output. This can allow us to easily identify the targets visually. Then we will loop through the result. Each item is a packet object, so we will extract the source IP of the reply packet. This will be the IP address of device, which is found to be online and reachable. Let's use a blue color for the IP address. Lastly, let's allow the user to pick an IP address from the list. Once an IP is chosen, we will use that as a return value for this function. Let's import the SCAPI classes and functions we used. Those will be the SRP function, Ether, and ARP classes. Let's quickly fix this syntax issue. Then on our main function, we need to call the ARP scan and store the result into a variable. And let's adjust the argument passed to the device class, since we will no longer get the target IP from command line arguments. Now let's test our changes. We will run similar command. Only difference is that we will pass a network address instead of an individual IP address. There are plenty of ways on how to get this. Typical method is to identify first the subnet mask of your IP, which you can see on the network interface settings. Let's fire this up. It is now sending ARP broadcast messages. And it returned an output. These are the IP addresses that responded to our broadcast message. That means they are online and reachable on the network. Although this gives us an easy way of finding online targets, this doesn't tell us what kind of device are they. To save time, bad actors typically only target personal devices such as mobile phones and laptops, and avoid others that is not relevant to their motives. In order for them to identify the device better, they use the MAC address OUI. If you recall, we also discussed this slightly on the first part of this video. So, how can we get that information and put it alongside with the IP address? Looking up the OUI via SCAPI is not as straightforward as other techniques. In the back end, it looks for Wireshark manufacturer database file which contains the OUIs. I don't think I have that on my installation, so let's try another way. There is a nice Python module called MAC vendor lookup that we can use as an alternative. In the back end, this gets the OUI database from my EEE site. I already installed this via pip, so we can import it right away. We need to import the MAC lookup function, which will perform the actual lookup. Then the vendor not found error exception, which we will discuss in a bit. Going back to the ARP scan function, we will extract the MAC address of the device. We can easily get it from the ARP layer as the HWSRC attribute. Then we will try to look up the MAC address using that module and store the result in vendor variable. If it cannot find it, we will just display unrecognized device. Now, the reason why we are catching this exception is because not all manufacturer OUI are registered to IEEE database. That means there will be cases where scanning tools like this will not be able to detect the proper vendor. Do note that OUIs are not perfect. Sometimes the database is not updated. For example, you might see a device appearing as a mobile phone, but in fact it's a laptop. And MAC addresses can easily be spoofed, so this adds another layer of confusion. But in normal circumstances, OUIs are still one of the ways on how bad actors footprint their targets. Now, to finish our program, let's display the MAC address together with the vendor OUI for a better device footprinting. Let's test the final changes. We will rerun same command. As we see, it was able to identify some devices. For example, we know that typically router IP addresses are either the first or last IP address on the network. But seeing that this is a TP-Link product gives us confirmation that this is really a router. There are also other unfamiliar devices like this one. This may also give attackers some motive to target this device further in order to get more information. Another one is this Synology product. Seeing this on the output will give us idea that there's some network storage device around. And as we just discussed, some devices may appear unrecognized, which is normal. I hope you learn a lot from this video. This shows that bad actors can get more information about our digital footprints in many ways, such as sniffing on our DNS traffic. So be aware of this and always protect your home network.